Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 13th, 2026, just 3 days ago. It introduces a method that reduces token usage by up to 93% and cuts the time to first token by 86% compared to standard video language models. The paper is titled CoPE-VideoLM, Codec Primitives for Efficient Video Language Models. And as we'll see later, these efficiency gains allow it to handle extremely long videos without sacrificing performance. Figure 1 illustrates the core difference in processing between the two approaches. In the top orange panel, existing methods decode every video frame into full images, which generates a dense, computationally heavy stack of red tokens. The bottom blue panel shows the proposed approach, which instead reads the raw compressed data, like motion vectors, to create a much lighter stream of blue tokens. Finally, the chart on the right confirms this efficiency, showing that the new model in blue achieves higher accuracy with 80% fewer tokens than the standard baseline in red. Well, Figure 2 details exactly how this codec-aware pipeline works step by step. At the bottom, the diagram breaks down the video input into its raw structure, known as groups of pictures, or GOPs. Each group begins with a complete iframe, followed by a sequence of p-frames that only store incremental changes like motion vectors. The real innovation happens in the middle layer. While the iframes go through a standard vision encoder to create a dense block of 196 tokens, the p-frames take a much lighter path. Their raw motion data is processed by a specialized delta encoder, which outputs just 8 compact tokens per frame. Finally, these efficient streams merge at the top, where the large language model fuses them with text instructions to generate an answer. So, while Figure 2 introduced the delta encoder as a single unit, Figure 3 opens it up to show the internal machinery. Inside the central gray block, the system splits processing into 2 lightweight branches. The top path compresses motion vectors using a simple MLP and a motion transformer. Meanwhile, the bottom path processes residuals using a ResNet 18 and a residual transformer. Finally, on the right, these compressed tokens feed into reference and warped transformers. This setup is crucial during pre-training because it forces the lightweight codec features to align perfectly with the standard visual embeddings from the image encoder. Alright, having covered the architecture, Table 2 presents the main results across general video understanding benchmarks. The rows are split between proprietary models at the top and open source models below. Focusing on the open source section, the proposed method, labeled Hours 7b, consistently ranks among the top 3, which are highlighted in green, yellow, and red. For instance, on the perception test, it achieves a score of 70.5, beating the LLAVA Video 7b baseline. This demonstrates that using sparse codec tokens can actually maintain or improve performance compared to processing full frames. Now, Table 1 and the accompanying plots break down exactly how this efficiency translates into accuracy gains. The table compares the model against the LLAVA video baseline at 3 different sampling densities, 1, 2, and 4 keyframes per group of pictures. If you look at the section for 4 keyframes, adding the compressed p-frame tokens boosts the perception test score to 70.5%. Crucially, this result beats the full 64-frame baseline shown at the bottom, even though it uses less than 20% of the total tokens. The charts on the right confirm this trend, where the blue line consistently floats above the red baseline, indicating higher accuracy for every unit of compute. Okay, while Table 1 demonstrated high accuracy, Table 5 proves the method is also much faster. The top row establishes the baseline for LLAVA Video 7b, which takes about 2.4 seconds just to produce the first token. In contrast, the section below for the proposed model shows dramatic improvements. For the 1 keyframe configuration, the time to first token drops to just 0.33 seconds. This 86% reduction makes the system far more responsive for real-time applications. Wrapping up, the key takeaway is that video compression offers a rich, untapped signal for AI. By processing raw codec data instead of full images, CoPE-VideoLM slashes compute costs by over 90% while maintaining accuracy. This could finally make real-time, long-form video understanding practical for everyone. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.